Hi, my name is Benjamin Capps. I'm an undergraduate student at Southwestern University studying computer science and mathematics. Over the summer of 2020, I did research under Dr. Jacob Schrum over using multiple generative adversarial networks to build better connected levels for Mega Man. The motivation behind my work last summer is that GANs have been shown to be an effective means of procedural content generation via machine learning. Additionally, previous work is based on generating individual segments of fixed size. The question I sought to answer was how to preserve the original structure of the levels such that the GAN-generated levels connect in a way similar to the original game. Previous work in Mario, for example, has been left to right generation without much regard for the level structure. However, with a game such as Mega Man, if the levels snake in such a way that if the segments are not placed in an intelligent way, it would be very difficult for the player to traverse. Work in applying generative adversarial networks to video games started in 2018 when Vanessa Volz, Jacob Schrum, and others produced work in generating Mario levels with GANs. Work in the area quickly took off with the generation of Doom levels using GANs, and shortly after that, a multi-step GAN training was applied to an educational video game. Then, work was done on GVGAI's Zelda using bootstrapping GAN to generate levels. J. Gutierrez and Dr. Schrum then used a GAN in tandem with a graphrammer to produce levels in Zelda. Also, levels in Mega Man, Mario, and Kid Icarus have been generated procedurally using variational autoencoders. The purpose of a GAN is to emulate the original training set. To accomplish this, it is trained in tandem with the discriminator, whose job is to determine whether the input is a member of the original training set or output from the GAN. During training, random latent inputs of an arbitrary fixed size are fed into the generator, and training completes when the discriminator's decision is no better than a guess, at which point the discriminator is discarded because it can no longer determine whether its input is from the original training set or from the generator's output. GAN training in Mega Man involved taking the text-based representation of the game from the video game level corpus and using it as training data. We collected the data by taking a 16 by 14 segment around the player's spawn and sliding it across one tile at a time until the end of the level. Each time the window was slid over a tile, that segment was saved and used as training data. From there, one of the segments from the training set was fed into the discriminator, and based on the fact that it was a member of the training set, the weights were backpropagated to better determine that that segment was real. Then, a random latent vector of length 5 was inputted into the GAN, which produced a segment that was served into the discriminator. Based on the fact that it was a fake segment, both the generator and the discriminator's weights were backpropagated, such that the discriminator is better at determining that that type of segment is fake, and the generator is better at fooling the discriminator. Just because the generator is capable of generating convincing fakes does not mean it's capable of generating a cohesive level. Due to this snaking pattern of Mega Man levels, not all inputs to the GAN produce meaningful output. The solution to this was to evolve the latent vector to generate beatable levels. We used multi-objective evolution via NSGA2 to maximize the solution path length, which was evaluated by A-star search, and the connectivity of the level, which represents the percentage of tiles that are reachable by the player. The baseline for our experiments is one GAN, which is a single GAN that's trained on all of the training data from the original game. Generation happens one segment at a time, where each segment is associated with 9 variables. So 5 of those variables are latent variables, which are fed into the GAN to generate the segment, and then 4 of them are direction variables, which are responsible for relating the segments to each other such that we get a snaking pattern in the level. Using only one GAN does not preserve the original structure of the segments, and the levels tend to lack cohesion. Not only that, but the levels also tend to have a great deal of wasted space, such as these two segments. Not only do these segments not serve a purpose, but if the player were to traverse down into them, they would get stuck and have to respawn in order to escape. Our response was to parse the data into different types of segments and train GANs based off of those different types of segments, such that whenever we call a GAN to generate a certain type of segment, it can consistently produce something that maintains a structure. So for example, we have a down GAN that's always responsible for generating a segment that's open on top and on bottom, and has some sort of way that you can fall through it. The lower right GAN is responsible for having an opening on top, some platform in the center, and an opening on the left. Similarly, horizontal, lower left, upper right, and upper left corners, as well as up GANs, were trained on the original data such that we can stitch them all together and always make some sort of cohesive level. Once again, we evolved the Realvalued vector using NSGA2 based on the A-star path length and connectivity, both of which were evaluated using the A-star search. We did 30 runs of each type, one being multi-GAN, one being one GAN, for 300 generations with a population size of 100 parents and 100 children. Each level was 10 segments long, 5 latent variables and 4 auxiliary variables, making a latent vector of 90 total variables. There was a 50% chance of single point crossover, and each real valued number in the vector had an independent 30% chance of polynomial mutation. This graph represents the average across all 30 runs, with the x-axis being the generation and the y-axis being the champion A-star path length. These were evaluated using a standard student t-test, and the error bars represent a 95% confidence interval. These results showed that the multi-GAN was capable of generating segments that were statistically significantly longer than one GAN by approximately 50 steps. This further supports the observation that one GAN levels tended to wasted space, often having either unreachable or pointless segments, whereas multi-GAN more effectively utilized its space. Although we evolved the levels to maximize A-star path length and connectivity, we also evaluated them for their novelty. So the novelty of a segment X with respect to a collection of segments S is the average distance between X and the other segments, the distance being how much that segment differs from the next. Level novelty takes in a level and is the average novelty across every segment within that level with respect to the other segments in that level. We found that when evaluating the VGLC levels, both the one GAN and the multi-GAN outperformed the VGLC in terms of novelty, but not statistically significantly so. And additionally, one GAN slightly outperformed multi-GAN, but again, not significantly. And then evaluating distinct segments by type, we found that one GAN produced the most distinct segments relative to the number of segments it produced, second by the VGLC, and then last was multi-GAN. In other words, multi-GAN produced the least number of distinct segments. Additionally, once again, we found that one GAN produced the most novel, and both multi-GAN and one GAN outperformed the original VGLC in terms of average novelty. Like I said, multi-GAN produced comparatively fewer distinct segments than either one GAN or the original VGLC levels. This was due to in large part of the lack of diversity in the corner GAN training set reflected in the corner GAN output. The novelty score and distinct segment ratio was strikingly worse from the corner GANs compared to the other GAN-generated segments. As a result, many of the corner segments seem similar when comparing against all other levels, though it's far less noticeable when actually playing a single level. We learned that multi-GAN is better at creating longer, possibly more cohesive levels that utilize more space than one GAN levels did. However, we also learned that one GAN was better at producing more novel and more distinct segments than multi-GAN. So we wanted to find a way to be able to play the levels to help qualify their differences and hopefully reach some conclusion as to which generation method is superior. So we settled on Mega Man Maker, which is a fan-created game engine that's really easy to create and edit levels. It's got a huge range of items and enemies, such as a platform gun, which allows the player to traverse over dangerous cliffs or pits without the need for permanent blocks to be placed there. And it allows us to play the game that mocks and mimics the original Mega Man game, but it is obviously a text editor, so we can upload our GAN-generated levels to this database and play them ourselves and conduct a human subject study. The study consisted of 20 participants, most of them who attended Southwestern University, and we gave them each 2 levels and told them that one or both of them may have been created by a human. They played one GAN level and one multi-GAN level. We used the online platform Mega Man Maker, and we asked them a series of questions, one of which was, did they complete the level? Another was, did they think the platform gun was required to beat the level, which was created by a human, which was harder, more fun, more interesting, more human-like. The results from the human subject study are as follows. 17 of the 20 participants completed the multi-GAN level, whereas only 14 of the 20 participants completed the one GAN. 8 of the 20 thought that the platform gun was required for multi-GAN, whereas 11 thought that the platform gun was required for one GAN. 13 of the 20 participants were fooled into thinking that the multi-GAN levels were indeed created by a human and not created by AI, whereas only 4 of the 20 participants were fooled into thinking that one GAN was created by a human. 14 of the 20 participants thought that one GAN was harder than multi-GAN, 6 versus only 6. 18 of the 20 participants thought that multi-GAN was more fun. 15 to the 20 participants thought that multi-GAN was more human-like, and 13 to the 20 participants thought that multi-GAN was more interesting. The values in bold are statistically significant based on a binomial test. And here are some of the participants' comments. So when asked why 1GAN was harder than multi-GAN, participants responded that 1GAN levels made no sense, led to nowhere, and the death screen. So when traversing through the level, there are some times when the 1GAN could fork two ways as a path, but one of them is certain death and one of them is not. So that's what they're referring to here. 1GAN levels seemed hard in a random and not very well thought out way. So some of the level structure doesn't really make sense because you could like go over to this part of the level and think that you should be able to get into this water segment, but you really can't. You're blocked off completely. And when you go down to this segment, you could go into the water segment, but it's blocked off. There's nowhere for you to go. You have to turn around and backtrack in order to beat the level. And they said that 1GAN levels seem to force the player to make a leap of faith at the start. And so a lot of 1GAN levels started off like this, where where you go off. And one thing to note is that players don't get to see the entire layout like we're seeing right now. They only get to see a 16 by 14 screen. And so when you're here, you don't know if there's an enemy or a spike beneath you. So you just have to keep jumping down and falling down 3 or 4 segments until you finally reach somewhere that you can start to traverse. And so that's sort of a commonality between a lot of 1GAN levels. When asked why multi-GAN was more fun, one participant said that they knew what they were going to do and could make things deliberately harder for them in an intelligent way, and there were many places they could go, versus 1GAN, where there were many places they could not go. When participants were asked why the 1GAN level was not as human-like as the multi-GAN level, they responded that it often spawns the player next to enemies, and it feels impossible not to take damage from them, which is not characteristic of a human-like level, which would progressively get harder uh, as the level progresses. Additionally, 1GAN seemed like it was entirely random and that it made it frustrating with solitary floating blocks in random places, such as these floating blocks here. And so these are making it seem random and not human-like because they serve no purpose and are useless so effectively. Whereas for multi-GAN levels, one participant said that it was more human-like because it had more repeated building elements, which is interesting because we found that multi-GAN struggled in diversity and had more non-distinct segments than 1GAN did. Um, and it seems, according to this participant, that that is a benefit, that more human-like levels have more repeated building elements, whereas non-human-like levels are more diverse. Additionally, one participant said that the multi-GAN levels knew what they were going to do and could make things deliberately harder for them in an intelligent way. And so this participant was referring to this exact level, in which it seems to be pretty easy at the beginning, where you can just simply fall down and traverse without much difficulty, until you get to more difficult jumping puzzles and enemies start spawning behind you, and you fall into what could be spikes. And the level progresses and gets more hard, like more difficult, and even blocks you off with some breakable blocks at the end. Additionally, one thing that's interesting about this level in particular is that despite these two segments being independent from each other, multivariable evolution allowed us to uh, seamlessly have a ladder that is cohesive between two independent segments. Through both quantitative and qualitative observation, we discovered that multi-GAN produces longer, more fun, and more human-like levels more consistently than 1GAN did. Additionally, our research supports the idea that using multiple generative adversarial networks is an effective way of preserving level structure during generation. However, 1GAN outperformed multi-GAN in terms of level novelty and distinct segments. Despite this, participants believed that the lack of repeated building elements resulted in a less enjoyable and less human-like experience. The 1GAN generation method consistently struggled to select sensible segments during generation, causing wasted space in the final evolved output and more novelty. As for future work, conditional GANs instead of multiple distinct GANs could be a beneficial way of consolidating training. With multiple GANs, each GAN has to be trained separately with the others with separate training data, whereas it would only take a single conditional GAN with a single set of training data with different IDs to preserve segment structure. Additionally, token-based one-shot arbitrary dimension GANs, also known as toad GANs, have been shown to be a reliable means of generating entire Mario and Mario Kart levels without the use of dividing into separate segments. So it may be beneficial for us to use that algorithm to also generate Mega Man levels. Additionally, compositional pattern producing networks have been shown to be a reliable method of generating levels with more consistent patterns, an attribute favorable to our participants. And finally, quality diversity algorithms such as map elites would allow us to evolve and bin different levels with broader desirable attributes such as number of enemies, number of ladders, and so on. Special thanks to the Summer Collaborative Opportunities and Experience, also known as the SCOPE program at Southwestern University. Without the donors' support, we would not have been able to conduct this research. Also, special thanks to Mega Man Maker, which allowed us to consistently play and conduct our human subject study. If you're interested in looking at or playing any of the Mega Man levels, this is the link that allows you to view or play them as you please. Are there any questions?